Okay, welcome back. We're going to do another example of evaluating a definite integral using the limit definition. This time we're going to be doing the integral from 0 to 4 of the function x squared, but we're going to be using left endpoints, again, regular partitions, so we're going to break the interval from 0 to 4 up into n equal pieces. Just a quick reminder, we're going to need to use some of these closed form summation formulas, all right, that we saw in the previous recording. All right, if you add up n ones, you get n. If you add up the sum of the first n integers, you actually get n times n plus 1 divided by 2. If you add up the sum of the first integers, n integers squared. If you didn't use it in the last video, we are going to use it in this one. You get n times n plus 1 times 2n plus 1 divided by 6. All right, let's take a look here. So I've got some of this typed out, and then we'll do some writing. So again, we're going to use left endpoints here. Again, we've got the function is x squared. All right, so notice our function, our integrand is x squared, so the function f of x we're talking about is x squared. Our interval is of length 4, so we're going to take that and divide that into n pieces. So our delta x value is 4 divided by n. As we saw in previous work, the special number that we're going to plug in, which we're calling x sub k star from the kth interval, it could be the first interval, the second, or the third, or the fourth. This variable, this dummy variable k, or dummy index k, helps us quantify the dot 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 when we think about the summation in the Riemann sum. What we end up getting for a left Riemann sum is that it's the value of the left endpoint of the kth interval. The kth interval, remember, is x sub k minus 1 is the left endpoint, and x sub k is the right endpoint. So we're taking x sub k minus 1, and that's just the left endpoint a plus k minus 1 steps of size delta x. Now, a is 0, so we just put in 0. Delta x is 4 over n. So we just get 0 plus k minus 1 times 4 over n. So we just get this value right here. K minus 1 in parentheses times 4 over n. Now, we're going to consider n to be a fixed integer. So we're going to drive that limit to infinity eventually, but we're saying, okay, let's write out what the Riemann sum is for n subintervals. Riemann sum is, as indicated here, the sum from k equals 1 up to n. So for each subinterval, we're going to pick a point, the left endpoint, plug it into the function f, multiply it by the width of the subinterval. Now, we're assuming we're talking about a regular partition. That means we don't have a variable subinterval width. Each of these subintervals is going to be with 4 over n. So delta x sub k is just going to replace by 4 over n over here. Now, we're going to plug in this value right here for x sub k star. That's going to go into our function. That's why we have that expressed down there. And it's keeping in mind that the function we're talking about is x squared. We just need to put that expression in and then do a lot of simplification and a lot of rewriting next. All right, so what do we get? We're going to square that expression. So we get the sum. All right, one thing we can do, well, let's just write it out and then we'll pull that factor out after. Okay, so we're going to get the sum from k equals 1 to n. We're going to square this quantity here. So k minus 1 times 4 over n squared times 4 over n. All right, we'll get to the squaring next. All right, so we're just going to square factor by factor. So we get k minus 1 squared times 4 over n squared. Well, 4 squared is 16, n squared is n squared is n squared, and then that's times 4 over n. We can drop the parentheses there now. Now, one move we're going to do next here, again, we saw this in some of our prior work. The sum is dependent on k. N is fixed for right now, and therefore these factors right here, which combine together to give you 64 divided by n to the third power, that's a fixed quantity temporarily here. So what we can do is we're going to factor that out of the sum. Again, remember, the sigma notation means you're adding up. So this is a common factor each term. You can factor it out of each term. So now we get 64 over n to the third power times our sum of k minus 1 squared. Now we need to square out that k minus 1. All right, I'm just going to do it, but keep in mind, I'm just going to write this kind of off to the side. k minus 1 squared, we would be multiplying the binomial. K minus 1 by itself, we cannot. There's no property of exponents that's going to apply here. We have to use the distributive property. If we do that, we end up getting k squared minus 2k plus 1. All right, now we're going to split this up into 3 summations. Okay, so we're going to leave the 64 over n to the third power there, and then we're going to have the sum from 1 to n, k equals 1 to n of k squared. So the sum of the first n integers squared. Now the minus 2, again, we could factor that out of the summation, so I'm going to do that in one step here. And then we're going to have the sum from k equals 1 to n of just the k part. Plus, again, we got that other sum we've got to consider there, which is the last sum. You don't want to forget about that one, just a constant term, but they still add up of the constant term 1. So we're going to be adding 1 to itself n times. Now again, this is the key, that if we're going to be able to implement the limit definition of the definite integral, we have to be able to get a closed form expression for the Riemann sum. Right now, we can do that because we know that this is adding up to n. The sum of the first n integers is n times n plus 1 divided by 2. The sum of the first n integer squared is n times n plus 1 times 2n plus 1, all divided by 6. So now we can replace those summation signs, the sigmas, with those exact expressions right there in a closed form. We can then do some more algebra to evaluate the limit as n goes to infinity. So we still have our 64 over n to the third power. Now we're just going to put in here what we just wrote. And then in the next, oh, I lost my minus 2 there. Hold on a second. So we got minus 2 times n plus 1 divided by 2 plus n. All right, little simplification we can do here. This 2 will cancel out. We do need to distribute the 64n cubed to each one of these terms here. So we'll do that in the next line. That's going to give us 64 times n plus 1 times 2n plus 1, all divided by 6. I'm just putting the number in the numerical factor of 6. That kind of came up small, which is in the denominator. Maybe not much better there. 6 in front of the n cubed, minus, then we're going to have 64 times n plus 1, all divided by n to the third power. And then the last term is going to be 64n divided by n to the third power. Okay, now our ultimate goal is going to be to not let n be a fixed integer, but let n approach infinity, take more and more and more subintervals, and then we know we're going to get closer and closer to our limiting value. Well, a little bit of simplification will show, okay, what do we have here? One of these factors will cancel with one of these factors. We got 64 over n to the second power. That's going to approach 0 as n approaches infinity. All right, so that last term is going to die off. Likewise, this is roughly speaking, we have n squared on top, n to the third power on the bottom. This is roughly speaking like 64 over n, which again, we know that's going to approach 0 as n approaches infinity. So the last two terms are going to kind of die off for us here. What happens to the first one? Well, we can do a little bit of simplification. One of the factors of n will cancel out, and that'll leave us with an n squared on top and an n squared on the bottom. And what we know about our limits as we're approaching infinity is if the power or degree on top for your polynomial is equal to your degree on the bottom, then it's going to be equal to the ratio of the leading coefficients as your value gets bigger and bigger. In this case, n gets larger and larger. So as n approaches infinity, this first expression is going to approach. Well, what are we going to have left? We're going to have just the coefficients. If we multiplied it all out, we would have 64 times 2 times n squared. So we're going to get 64 times 2 on the top. On the bottom, we're going to get just 6. All right, so that's going to be our answer. And I'll just clean that up a little bit. 2 goes into 6 3 times, so that's going to be our final result. All right, so I'm just going to rewrite this all a little bit. So again, key steps, let's just back up a little bit, was to after we figured out the expression for x sub k star, in this case was the left endpoint, figured out what delta x was equal to, then we plugged it into the function, and now we're just did some algebra to expand it out, then use properties of summations, and then the special closed formulas, closed sum formulas to get this as one exact expression. Then we just take the limit as n approaches infinity, and we end up with 64/3 in this example. All right, so just tying this together here, we started out with the integral from 0 to 4 of x squared dx. That's going to equal the limit, and because we're using a regular partition, we could say its limit as n goes to infinity of our summation from k equals 1 to n of f of x sub k star times delta x. Again, delta x is not a variable, it's fixed in this example. And that came out to, after all of our work, just going to go back up and we'll look at it and we'll put it back in, this expression here. All right, so we're basically just going to copy that down. I might copy it down in a little bit of a simplified form. Then I'll double check it. 64, and then it was times n plus 1 times 2n plus 1, all divided by 6n squared. And then the second term, I'm just going to scroll back up for a second here, was really, if we cancel out one of these n's, it would be 64 times n plus 1 over n squared. Sorry, minus. Then it was plus 64 over n squared. All right, and as we just showed a minute ago, the last two terms approach 0, and this limit right here comes out to 64/3. So again, we got a nice string of equal signs here. Definite integral is equal to that limit of the Riemann sums. Limit as n approaches infinity of the Riemann sum, and that has a nice formula that we can compute. And so we end up getting 64 divided by 3. All right, I'm just going to draw the picture, sketch the figure of this area that we just computed, because keep in mind that the definite integral corresponds to an area under curve. So we're talking about just the function x squared, which we're used to. So here's a sketch of that. We wanted to compute the area from, say, 0 to 4. All right, so this is not like the first example where we could verify this. I don't have a great picture of the parabola here, but this is not a triangle or anything that we're used to geometrically. All right, so we had to do it this way. This is one way to compute this area under the curve, under the function we're talking about here. And again, this function is x squared.